Good morning, everyone. So today we are going to start looking at the last topic that we will be discussing in this course, that is natural proofs. And in particular, maybe I should just call it, instead of natural proof, it's more apt to call it as natural proof barrier. Okay. So what do we mean by natural proof? What is natural proof barrier? So first we are going to understand these words and why this is so important to the study of circuit lower bounds. Okay. So before we get started with natural proof barrier, so let me give a little bit of motivation as to why this thing came up. So in the 1980s, so when researchers came up with this various circuit lower bounds, so starting with circuit lower bound for parity, the result was first, as we discussed, was shown by Aktay, first Sachs, Sipser, followed by Hastad's result, then Razborov-Smolensky's proof. Okay, and after that, Razborov also showed that you can give monotone circuit lower bounds for the clique problem. Okay, so there were these various circuit lower bound proofs which came up, and not only these, there are other circuit lower bounds also. So most of these circuit lower bound proofs, so the various circuit lower bound proofs, okay, led researchers to believe that this could be a tool for separating, let's say, NP from P/poly. Okay, so the goal of course is to understand the P versus NP problem, and if we look at the circuit version of this problem, so if not separating P from NP, can we at least separate NP from P/poly? In other words, can we, let's say, take a candidate NP function, let's say SAT or any other NP hard problem, and show that it does not contain polynomial sized circuits. Okay, so that was the goal, and people started believing in 1980s that maybe if we extend these techniques, okay, these various techniques, if we can kind of refine this technique, maybe it would lead to solving this problem. Okay, but as of now we know that none of those techniques work. So how does a general lower bound technique work? Okay, any of these techniques, let's say Hastad's result or Razborov-Smolensky or whatever. So the way it works is that let's say we took a circuit class. Okay, so let's say we have a circuit class C, and we show that well, we take a function f and we show that a function f has some property, let's call it as P, but no circuit family in C has the property P. That is how usually the thing went about. I mean, if you look at Hastad's result, so Hastad showed that, well, I mean, one way of looking at it is that, well, if I take the parity function, then even if I restrict all but one variable of that function, the function can compute parity. The function is not constant with high probability, with probability half. I mean, even one variable, if it is alive, it can kind of change the value of the output by a probability half. On the other hand, if I take AC0 circuits, okay, then well, if I actually restrict all but one variable, in fact even if I restrict not just one variable, but even if I restrict all but n to the power epsilon many variables, the function actually with very high probability becomes constant. Okay. So it kind of shows that, well, if I look at that property P to be something of that nature, then it is separating parity from my class AC0. So this was the idea, and even Razborov Smolinsky also had a similar idea, and so on. So what Razborov and Rudich in the 1990s, so this was in 94. So what they tried to see is that, can we formalize this technique, and what can we say about this technique? Okay, so basically after all these results in the 1980s, they were still unable to show NP is in NP is not contained in P/poly. Okay, so then they thought that, okay, then what about the other side? Can we show that these techniques do not suffice? And that is the motivation for this natural proof barrier. So what Razborov and Rudich did was, in 94, they showed that these techniques most likely won't work. Okay, so we will discuss what we mean by most likely as well, and we will have to formalize what we mean by these techniques. And of course, won't work means that it doesn't separate. Okay, so this is going to be the what we are going to see. Most they won't separate NP from P/poly. Okay, so this is kind of like the holy grail that we have right now. We want to separate NP from P/poly, and this is something that this is the strategy what we would like to use in order to separate this. So after all these failures, Razborov and Rudich kind of thought that I would like, what if we show that it doesn't suffice? And then they came up with answer to that, and they showed that most likely this kind of technique will not separate NP from P/poly. Okay, so let's start with, we need to define, we need to kind of formalize a lot of things over here. So let's start with that. Okay, so let f of n be the set of all functions, all Boolean functions on n variables. Okay, so f of n is the set of all functions f such that f is a function from 0, 1 to the power n to 0, 1. Okay. And now we will define what we mean by a property. So a property is actually something very simple. Property is just something which is a map from f of n to 0, 1. Okay, whether a function has a property or doesn't have a property. Okay. So a called a combinatorial property. A combinatorial property P is a, yeah, so in this discussion, whenever we use the notation P, it is usually for property. Okay, it's not for the class P. Okay, just to make it unambiguous. I mean, I don't think we will be talking about the class P so much over here. Yeah, if we talk about, I'll of course mention it, but whenever we mention P, it is the property. A combinatorial property P is a subset of f of n. Okay, and another way to look at it is that alternatively P of some f is equal to 1 if and only if f belongs to P. Okay, so here I am kind of abusing the notation P and think of P as a function. This is the most natural way to look at it. So now we will define what is a natural. So P is any property. Okay, so now we will define what is called a natural property. Okay. P is, and one more thing that we should mention over here. So when we talk about property and we say that P is a subset of f of n, actually what I mean is that you should think of that property also as a family of properties or a family of functions. Yeah, okay, because see, fn is basically all functions on n variables. Now when I say P, actually what I am referring to is P of n. Okay, so maybe I should write it this way: combinatorial property P, okay, for n greater than or equal to 0. So for all values of n, P of n is a subset of f of n. And then when I say this, what I mean is that Pn f of n, if and only if f of n belongs to P of n. This is the definition, yeah, of a property. So P is natural if it satisfies the following three conditions. First is that there exists a polytime algorithm that takes the truth table of a function and decides if of a function, let's say f, and decides if P of f is equal to 1. Okay. Now when I say polynomial time algorithm, so note that, so this property is called constructivity. Okay. So when I say polynomial time algorithm, so one must note here that the running time of this algorithm is of the order of 2 to the power order n, right? Because the truth table itself has size 2 to the power n. Okay, so it is polynomial in the truth table because the algorithm actually takes any truth table and it says whether that function has the property or not. This is constructivity. Let me write this as 1. The second property is largeness. So the number of functions which have P of n is quite large, that is 2 to the power minus on of f of n. Okay. This is largeness. So here once again note that what is the size of f of n? It is 2 to the power 2 to the power n, right? So when I say that Pn has size at least 2 to the power minus order n, it is actually quite large in this as a function of this set or this size. And the third thing is usefulness. So okay, So we say that Pn is P/poly useful if okay, for a family of functions f of n Pn of f of n is equal to 1, then f has super polynomial circuit size. Okay, let's understand this. So this is called, this property is also called usefulness. Okay, so usefulness is important because the property has to be something which is actually able to separate that function from P/poly. What is it saying is that, so suppose if I have a family of functions, and if I say that that family of function is or let's say if I have a property Pn, okay, so the property is P/poly useful if there is some I mean, if for all family of functions that satisfy the property, that function should have super polynomial circuit. Okay, in other words, that function cannot be solved by in P/poly. Okay, so that is the thing. Now let's look at the other thing. So constructivity essentially means that the property should be easy to implement. Okay, it should be easy to use that property. In other words, any polynomial time algorithm can take a function and decide whether the function has that property or not. Okay, so any again, so it is it's the input, so that is my input over here. So in terms of, it's in terms of 2 to yeah, it's polynomial in terms of 2 to the power n. So if I look at it in terms of n, then the time is 2 to the power order n. So I just wanted to mention. So it is not polynomial in n, but it is polynomial in the length of the truth table. Because yeah, I mean, you know, in order for an algorithm to decide the property P, it needs the entire truth table. It needs the entire function. And largeness is again important. The motivation for largeness is that, well, if you have, so it kind of says that, well, most functions should have that property. Okay, or not most functions, it's not of course most, but a large fraction of the functions, a significantly large fraction of the functions should have that property. Okay, so now what is the result? Okay, so let me state the theorem of Razborov and Rudich, and of course we'll come to the proof of this theorem later on, but just to get a picture of where we are going. In fact, some of the notations that we use in this theorem we haven't yet defined, but we'll define it very soon. Okay. So there is no natural proof of super polynomial circuit lower bounds unless we have that h phi is 2 to the power k to the power epsilon for every pseudo random generator phi from 0 1 to the power k to 0 1 to the power 2k in p slash poly. Okay. So let's just try to understand this. What this thing is saying is that, well, now, okay, first of all, what do I mean by natural proof? So natural proof is essentially a proof which is using a natural property in order to prove circuit lower bound. Okay, so that is what we mean. So there is no natural proof of super polynomial circuit lower bound unless this happens. Now what this is saying is that if there is a natural proof that is able to show circuit lower bound, that is able to show a super polynomial circuit lower bound, in other words, if there is a natural proof which is able to separate NP from P slash poly, then what we get is that, so h of phi is kind of the hardness. So we'll define what h of phi means very soon, but essentially this kind of quantifies the hardness of this function phi. Okay, we'll come to it. So essentially what it is saying that if a natural proof of this exists, then this pseudo random generator is not very hard. Okay, so the hardness is bounded by 2 to the power k to the power epsilon for every pseudo random generator phi that belongs in P slash poly. For every pseudo random generator where the parameters are, so it takes a k bit string and maps it to a 2k bit string and belongs to P slash poly. So this is essentially the theorem of the theorem that we are going to see. So when I said that most likely, this was the condition, and this is something that is not believed. So it is not believed that a pseudo random generator in P slash poly will be will not be hard. Okay, so it is believed actually that the pseudo random generator is hard, because if a pseudo, so what is a pseudo random generator? So a pseudo random generator is something that is, of course, generating a random string. Now if a pseudo random generator is not hard, then, well, it kind of means that one way functions do not, I mean hard one way functions do not exist, and many cryptographic applications, they are kind of based on the assumption that one way functions exist, hard one way function exists. So there are functions which you can use to kind of encode something, and of course you cannot decode it back. Okay, so it is based on the principle that hard one way functions exist. So if actually this condition is not true, then it will kind of break many cryptographic protocols, right? So this is something that is believed. Okay, so if there is a natural proof of super polynomial circuit lower bound, then this condition is getting violated, and that is something which is not believed to be true. Hence, most probably natural proof does not work to show super polynomial lower bound. Okay. So this is the intuition of what we are going to show. So now let's try to understand it. So any question at this point? So now let's look at some examples, okay, just to kind of motivate this natural property. So first of all, if we look at Hastad's proof of separating parity from AC0, let's try to see why that's a natural proof. Okay, so essentially what the property that Hastad uses is that if we randomly restrict, let's say, n minus 1 variables, in fact much lesser than n minus 1 variables also, but let's keep it as n minus 1 variables, then of f, then f is not constant with high probability. Okay, so suppose this is the property that I defined for a function, that for a function f, if I randomly restrict, let's say, n minus 1 variable, then the function is not constant with high probability. Now, if I look at the parity function, so p of the parity function is actually 1. So, this property is true for parity. And what we showed, or what Hastad showed, is that for AC0, okay, so if I just use this notation, so AC0 is not, or not just this, so it's more precise. So, for all g in AC0, p of g is equal to 0. So, no function in AC0 satisfies this. So, basically it showed this by reducing it to bounded depth. It showed that, well, you can actually, if I keep on doing this restriction, I can represent the function as CNF or DNF form, and then it is with very high probability the function becomes constant. Okay. So, this was the one that Hastad used. Now, this property, of course, by this idea satisfies the usefulness. Now, why is it constructive and why is it large? So, to see constructivity, note that I can actually, given the truth table of the function, I can actually enumerate all possible restrictions. Okay. So, enumerate all possible restrictions and check if the function becomes constant. Okay. So, this shows constructivity. Now, to see, yeah, so this would check if a function has this property. To see largeness, once again, why should most functions have this property? So, oh, again, yeah, so most functions should have this property because once again most functions, I mean the restriction of most functions are not constant. Okay. Or so a random function does not have p with high probability. Okay. So, of course, see, all these points need proof. This is easy to check, but to argue that a random function does not have this property with high probability, it of course needs a small proof, but this is not very difficult to see. Okay. So, essentially what this shows is that the strategy that Hastad used is a natural property, and the proof, I mean the proof of this theorem is actually not difficult. Okay. So, the proof of this theorem is actually quite easy. The majority of this paper, the paper by RazborovRudich, is actually dedicated to showing that these various circuit lower bounds which were shown till that point are actually all natural proofs. Okay. So basically Hastad's proofs, Razborov-Smolensky. Okay. Then there is another lower bound that we had discussed, Andreev's lower bound. So this Andreev function, and then we show that it has a I think 3n lower bound, something like that, 3n minus small o of 1. So all these proofs that were shown are actually natural proof strategies, and therefore yeah.